Hello students, this is Vishal sir from Ikra High School. Today we will be continuing Standard 9 NCERT syllabus Chapter 8 Motion Part 2. Let's begin with the graphical representation of motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of one-day cricket match, vertical bar graphs show the run rate of a team in each over. As we have studied in mathematics, a straight line graph help in solving a linear equation having two variables. The graphs can be better understood as it is a graphical representation and it is a pictorial representation that presents the data in a very simpler manner. To describe the motion of an object, we can use line graph. So, what are we going to use? Line graph. In this case, line graph show dependence of one physical quantity such as distance or velocity on another quantity such as time. In physics, in this chapter, in motion, we are going to study about graph with relation to distance and the other term would be time. Also, we would be studying about velocity and time. That we are going to show on distance time graph. Distance time graph. The change in position of an object with time can be represented on distance time graph. So, you can understand the change in the position of the object with respect to time. In this graph, time is taken along the x-axis. So, when you draw distance time graph, the time should be taken along the x-axis. The horizontal bar on the graph is called x-axis and the vertical bar on the graph is called y-axis. Both the horizontal and the vertical bar intersect at a point called origin, and this from here we can say that is the initial point of any object traveling with some speed in some interval of time, and distance is taken along the y-axis. Distance time graph can be employed under various conditions where object move with uniform speed, non-uniform speed, remain at rest. So, what type of things can you understand from distance time graph? You can understand whether the object is in uniform speed, non-uniform speed, or is at rest. These three things you can understand after looking through distance time graph. We know that when object travel equal distances in equal interval of time, it moves with uniform speed. This shows that the distance traveled by the object is directly proportional to time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line. So, here you can see the graph of an object traveling with uniform speed. It covers equal distance in equal interval of time. Here you can see a straight line object traveling with uniform speed shows a graph like this. The portion OB of graph shows that the distance is increasing at a uniform rate. OB is this part. This is O and this is B. This line shows that it is traveling equal distance in equal interval of time. Note that you can also use the term uniform velocity in place of uniform speed if you take the magnitude of displacement equal to the distance traveled by the object along the y-axis. We can use the distance time graph to determine the speed of an object. To do so, consider a small path AB of the distance time graph shown in figure 8.3. Draw a line parallel to the x-axis from point A and another line parallel to y-axis from point B. These two lines meet each other at a point C to form a triangle ABC. Now the graph AC denotes the time interval T2 by T1 while BC corresponds the distance S2 minus S1. We can see from the graph that the object moves from the point A to B. It covers a distance S2 minus S1 in time T1 minus T2. The speed V of the object therefore can be represented as V is equal to S2 minus S1 upon T2 minus T1. We can also plot the distance time graph for accelerated motion. Table 8.2 shows the distance traveled by a car in a time interval of 2 seconds. If you want to determine the speed of the object, we can determine from the graph itself. The only thing that you have to do, you have to draw a parallel line here this part to the x-axis and a parallel line here with the y-axis. These two intersect at a point. After that, you have to draw another line parallel to x-axis, and that should intersect at point C, and here you can see triangle ABC has formed, correct? So this is the time t1 minus t2, and this is the distance displacement s1 from C to B. It has covered from C to B, s1 and s2. So s2 minus s1. What you have to do? You have to subtract the distance s2 minus s1, and you have to subtract the time t2 minus t1. And if you find the ratio of s2 minus s1 upon t2 minus t1, you will find the speed of the given object. Here you can see another graph of distance time graph, and that is a little curvilinear, that it does not show a straight line, but it shows some part of curvilinear. Curvilinear graph always shows non-uniform motion, and when it is a non-uniform speed, you can say two to three things from the same graph. First thing, if you see from 0 to 2, the speed of the object has increased with a slow pace, while from 2 to 4 it has increased with greater pace compared to 0 to 2, and from 4 to 6 you can see it has increased a lot. That shows that the increase of the speed in the initial stage was slow, while after 4 it has increased constantly. So this shows two things. First, it is a non-uniform motion, that means the speed will not be constant. Second thing, the slope shows how may be the speed of the object. It may be slower in the initial stages, than it has increased after some time duration, and it has kept on increasing as the time passes. The distance time graph of the motion of the car is shown in figure 8.4. Note that the shape of the graph is different from the earlier distance time graph. For uniform motion, nature of this graph shows non-linear variation of the distance traveled by the car with time. So what does this graph signify? This graph signifies that the distance covered by the car in the given time is non-linear, it is non-uniform. Thus the graph shown in 8.4 represent motion with non-uniform speed. Velocity time graph. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. So if you compare this graph, this is velocity time graph. On y-axis you will find velocity, that is speed with direction, and on x-axis you will find the distance, the time covered by the object. Here you can see the velocity of the car is 40 km per hour at some point A. It is still 40 km per hour at some point B after it has traveled time t2. At time t1 it was 40 km per hour. At time t2 it is also the same velocity has been maintained, that is 40 km per hour. This shows that the object traveled uniform velocity, correct? So it is traveling with a uniform velocity. If the object moves at uniform velocity, the height of the time velocity graph will not change with time. It will be straight line parallel to x-axis. So if the object moves at uniform velocity, the height of the velocity time graph will not change with time. The height will not change. Here you can see the height has changed. It moves with a uniform speed, the height has changed. But in this graph, the height has not changed. It has remained parallel to the x-axis. Figure 8.5 shows the velocity time graph for a car moving with uniform velocity of 40 km per hour. We know that the product of velocity and time given displacement of an object moving with uniform velocity, area enclosed by velocity time graph and time axis will be equal to the magnitude of the displacement. To know the distance moved by the car, here what did you find? You found the speed of the car. To know the speed of the car, you needed to find the ratio of the distance traveled and the time taken. So at that moment you found the speed of the car, but here if you want to find the distance traveled or the displacement covered by the car, that should be the area covered by the car. Okay, we know that the product of velocity and time gives displacement of an object moving with uniform velocity. What is it? The product of velocity and time gives displacement. The area enclosed by velocity time graph and the time axis will be equal to the magnitude of the displacement. So if you observe this diagram, if you find the area of A, B, C, D, what you will find? You will find the displacement covered by the car. How much displacement has it done? You can find by finding the area enclosed by a certain figure. Here the figure is rectangle. So this is length, AB is the length and BD is the breadth. So length into breadth will be the area of the rectangle and that will be equal to the displacement covered by the car. We can also study about uniformly accelerated motion by plotting its velocity time graph. Consider a car driven along a straight road for testing its engine. Suppose the person sitting next to the driver records its velocity after every 5 seconds by noting the reading of the speedometer of the car. Velocity of the car in kilometer per hour as well as meter per second at different instant of time is shown in table 8.3. Here you can see at 0 second the car was having velocity of 0 meter per second or 0 kilometer per second. At 5 seconds it was having the velocity 2.5 meter per second or 9 kilometer per hour. Then at 10 seconds the velocity has increased to 5.0. That means it has doubled from, the time has also doubled from 5 it became 10 every 5 seconds. Okay, and the same amount of velocity has been improved in the second stage. Here also you can see instead of 9 km hour, the car speedometer shows 18 km per hour. Let's move further. Let's go 5 seconds more. Then at 15 seconds, at every equal interval of time, you can see equal velocity of the car is been noted, 2.5 and 5.0 and again 7.5. So the velocity is increasing at a rate of 2.5 meter per second or 9 kilometer per hour. That shows that the car is moving with uniform accelerated motion. In the case velocity time graph for the motion of the car shown in figure 8.6, the nature of the graph shows that velocity changes by equal interval in equal amount in equal interval of time. Thus for the uniform accelerated motion, velocity time graph is a straight line. So whatever you are seeing over here in this 8.6, that is uniform accelerated motion. And you can see the blue part over here. Here you can see a triangle ADE and a square ABCD. Okay, these two diagrams are there. If you find the area of these two highlighted part, what you will get? You will get the distance covered by the car. You can also determine the distance moved by the car from its velocity time graph. The area under the velocity time graph gives the distance moved by the car in a given interval of time. So the area of ABCD is equal to area of rectangle ABCD plus area of triangle ADE. Area of rectangle is AB into BC, that is length into breadth, and area of triangle is equal to half base into altitude. And you have to sum up both the areas and then only you will have the displacement covered by the car. In the case of non-uniform accelerated motion, velocity time graph can have any shape. Now let's begin another topic, that is equation of motion by graphical method. These three are the equations that you have to study while you study motion. This is the final velocity. If you see V is equal to final velocity, that is equal to initial velocity u plus acceleration into time. That is the first equation of any object to be taken in motion for graphical method. Then you have displacement or distance. S is equal to displacement or distance, and that is equal to ut plus half at square. Also 2as, twice acceleration into displacement, is equal to v square minus u square, square of final velocity minus square of initial velocity. Now let's go through another topic, equation for velocity time relation. So consider the velocity time graph. This is velocity time graph, this one. Consider velocity time graph of an object that moves under uniform acceleration. From this graph you can see that the initial velocity of the object is u and then it increases to v. So it has increased from u to v at point B, and at point A that is u, and at point B is v. So this is the increment of the velocity from A to B. This is v. Here you can say this is the final velocity that you are going to study, that is v. In figure 8.8, the perpendicular line BC and BE are drawn from point B on the time and the velocity axis respectively, so that the initial velocity is represented by OA, the final velocity is represented by BC, and the time interval T is represented by OC. BD is equal to BC minus CD. So what is BD? From B to D, this distance from B to D is equal to total distance B to C minus CD. Okay. So BD is equal to BC minus CD. Represents the change in velocity in time interval T. Let us draw AD parallel to OC. From the graph we observe that BC is equal to BD plus DC. Also the total distance BC is equal to, here they are writing BD is equal to BC minus CD, then the total distance BD minus BD is equal BC is equal to, from B to C you can see two parts, first part BD, second part CD. If you add both of them you will get BC. Substituting BC is equal to V and OA is equal to U, V is equal to BD plus U, BD is equal to V minus U. From the velocity time graph, the acceleration of the object is given by A is equal to change in velocity upon time taken. So what is acceleration? That is change in velocity and the time taken for changing that velocity. So this is the change in velocity. It has changed from U to V, and the time it has taken is from A to D. So acceleration is equal to change in time upon time taken, change in velocity upon time taken, that is BD upon AD. Change in velocity, how much is change in velocity? Change in velocity, you can see here, this is change in velocity. It was initially at this stage and it has increased over this. Okay, BD upon AD, and the time taken is AD, and AD is parallel to OC. What is OC? That is the time taken for gaining this velocity. So OC, instead of AD we will be writing OC. So that is equal to BD upon OC. OC is equal to time, A is equal to BD upon T. Now if you substitute T on the left hand side, it will become AT. BD is equal to AT. That would be one equation. That equation would be using equation 8.8, which is 8.8, BD is equal to V minus U. This is the first thing that you got, and second thing that you got, BD is equal to AT. You have to equalize both of them. BD is equal to V minus U plus is equal to AT. So what they have done, they have taken U that was negative on another hand side, substituting that part. So U is equal to U plus AT is equal to V. That is the equation that you obtained, and this equation is the equation for velocity time relation. Now position time relation. Let's take another point, position time relation. Let us consider that the object has traveled a distance s in time t under uniform acceleration a. In figure 8.8, the distance traveled by the object is obtained by the area enclosed within OABC under the velocity time graph AB. Thus, the distance s traveled by the object is given by s is equal to area OABC, which is a trapezium, area of rectangle OADC plus area of triangle ABD. So for position time graph, if you want to know the position of the object, that is the displacement it has covered, you have to find the area of the enclosed part. Here in this graph, you can see there are two areas. First area is ADB, that is a triangle. Another is AOCD, that is a rectangle. If you combine both of them, it becomes a trapezium. And if you find the area of this trapezium, this part, that will show you the position time relation. Area is equal to OA into OC, that is OA into OC, that is length into breadth, that is for this part AOCD, okay, and half AD into BD, half AD into BD, half base into altitude, that is the formula to find the area of the triangle. Substituting OA is equal to U, OC is equal to AD, that is equal to time T, and BD is equal to AT. Now we have to substitute all the formats over here. Okay, what is OA? That is U. OA is U, that is the initial velocity. OC is equal to AD, that is T, and BD is equal to AT. So what you will get, S is equal to the distance S traveled by the object is given by displacement is equal to UT plus half AT square. Equation for position velocity relation. From the velocity time graph shown in figure 8.8, the distance S traveled by the object in time t moving under uniform acceleration A is given by the area enclosed within the trapezium OABC under the graph. That is, S is equal to area of the trapezium OABC. OC is common in OA and BC, so they have written in distributive law. And now substituting the value of OA, BC and OC, OA is equal to U, BC is equal to V and OC is equal to T. From the velocity time relation that you came to know, time is equal to acceleration is equal to final velocity minus initial velocity upon time, that they are substituting time on left hand side and substituting acceleration on right hand side. So time is equal to this. So instead of this time you are going to write this. So you will write like this, V plus U, that is from this part, and for T V minus U whole upon 2 was here and A was here, they will be multiplied like this, and that is equal to S, that they are substituting on the left hand side. You will get 2AS is equal to V square minus U square. How you got V square minus U square? Algebraic expression of A plus B into A minus B. Now what is uniform circular motion? When the velocity of the object changes, we say that object is accelerating. The change in velocity could be due to change in its magnitude or direction of the motion or both. So let us consider an example for the motion of the body along a closed path. Figure 8.9a shows the path of an athlete along the rectangular track ABCD. Let us assume that the athlete runs at a uniform speed on a straight path AB, BC, CD, DA on the track. In order to keep himself on the track, he quickly changes his speed at the corner. So what does he does? Let us assume first thing that the athlete runs at the uniform speed on a straight path, okay, but in order to keep himself on the track, he quickly changes the speed at the corners. So in rectangle, he had to change the speed at ABCD 4 points. How many times will the athlete have to change his direction of motion while he completes one round? It is clear that to move in a rectangular track, he has to change his direction of motion 4 times. Suppose instead of rectangular track, the athlete is running along the hexagonal shape path ABCDF. Correct? Now we are moving from rectangle to hexagon, and here you can see the athlete have to change the direction 6 times to complete one round with uniform acceleration. So it is observed that as the number of the side of the track increases, the athlete has to take the turns more and more often. If the athlete moves with a velocity of constant magnitude along a circular path, the only change in his velocity is due to the change in direction of motion. Motion of the athlete moving along a circular path is therefore an example of the accelerated motion. Every point on a circle is a point where the athlete has to increase his speed and he has to change the direction. Only then he can perform uniform accelerated motion. The circumference of the circle of the radius is given by 2 pi r, and if the athlete goes in t second, the speed is equal to 2 pi r upon t. So when an object moves in a circular path with uniform speed, its motion is called uniform circular motion. Thank you.